Good afternoon, everyone. I hope you guys are doing very well. In this lecture, we're going to be discussing about state machine. This is a very important topic in VLSI, and in general, those who are doing electrical engineering or would like to get expertise in digital circuit design, uh, they should have familiarity or expertise in state machine design. This is not a very difficult as such, but yes, the precautions need to be taken in order to correctly design the complex circuits. So let's try to understand what are state machines. Let's say we have, we use logic gates, AND gate, OR gate, NOR gate, a bunch of gates we have, and we can say combinatorial logic. And then we have memory elements, which have the capability to store the state of a digital circuit. Okay. Now, what essentially is the state machine? Basically, it's the combination of the two. The combinatorial logic part, it is doing the job of input encoding, or say state machine encoding for the state machine, in which state your circuit is, and also decoding for the output, right? So we have certain inputs and certain outputs, and those are connected. So as you can see, the combinatorial logic generated logic inputs goes to these memory elements, which store the state of the circuit. Okay, and the state of the circuit can be changed on a rising edge of the clock. So here we are talking about the sequential circuit design. All right, and the output of these memory elements, or the state, can be used along with the inputs to generate the outputs for particular state, right? So this is a very simple general idea about state machine. No matter whether you have a smaller circuit or a bigger circuit, more or less you're going to be looking at these two blocks. One is combinatorial logic and one is sequential logic blocks, where memory elements like registers, okay, D flip-flops, or any kind of other flip-flop, but D flip-flops are de facto industry standard. So we're going to be talking about D flops here, and we can say, okay, this is input D0, input D1, and Q0 and Q1. So notice here, the Q0 tells the state in which the circuit is, and D0 basically is the state on the next clock edge, or what will be the next state. Okay, so that's a clear understanding. All right, now think when you're gonna design a state machine, think in terms of two elements: combinational logic for operations, okay, like arithmetic logic operations, for example, and your memory elements for storing the state. Okay, and there are two particular variants of state machine design or in practice. There may be other variants, but more or less those are based on these two major distinctions of the machines: Mealy machine or Moore machine. You may mix up these two variants, but in general, at a fundamental level, we talk about Mealy and Moore machines. Okay, so we're going to be looking at these two machines with some examples. All right, so let's try to understand what is the difference between these two kinds of machines, or these two kinds of state machine models. Okay, so as you can see, we have this in general state machine. So what happens? Let's try to understand Mealy machine. What happens in the Mealy machine? In the Mealy machine, the output logic. Okay, so output logic, which generates the output in any state, takes the input, actual input vectors, okay, and in what state your circuit is. So external inputs as well as the states becomes the input for deciding the output logic, okay. Or we can represent it in other ways, say let's say X are your inputs and Q1, Q2 are states of these two flops. So output would be the function of X, Q1 and Q2. So that's a Mealy machine, okay. So notice here that your output is not registered. It would be a combinatorial logic based because there is you are directly using the input, okay, along with the state outputs, okay. Now let's take a variant Moore machine. So the Moore machine is very similar to Mealy machine. Only the difference is that the output logic now it does not include the input. The output of a state is dependent on only on the state inputs, or y, that is output, is a function of state inputs, okay, in which state your circuit is. So that's the basic difference. Now there are stronger implications because of this little difference. What it is? Well, Mealy machines, as we can see here, they directly make use of input to produce the output, tends to have less states, okay. What does it mean by less states? Well, we're gonna use less number of flip-flops, okay. So we need to store states somewhere, okay, and we do use registers or flops, memory elements, to store the states of your digital circuit. So think about, if you have more states, you have to use more flops. If you have less states, you can get away with the less flops. Now that implication goes on to timing as well, because if you are going to use more flops, that will have impact on timing, a bit slower circuit compared to your combinatorial block, combinatorial logic, okay. So basically, if you are using all combinatorial block, you can just get the output on the next clock edge. But with the memory elements, then you have to check, because flop produces output, you can make use of that output only in the next clock edge. So there is a little implication there, okay. Now there is the advantage of uh, getting the registered output or output dependent on the state of flops, as in the Moore machine, that that you don't have to worry about asynchronous signal feedback into your circuit, okay. These are registered outputs, Q1 and Q2. Another difference is that in Moore machine, because the output changes on every clock edge, okay, these are safer to use compared to Mealy machine, because in Mealy machine, if say for example, if there is a glitch on any input, your output will have a glitch. So you need to make sure that your output doesn't have any glitch if you're sending this output to another block which is running at different clock, or in general if you are using the output as a feedback to the circuit. So you must have to synchronize before using it, otherwise glitch will propagate and your circuit will not work, okay. So different situations you may make use of these state machines. If you have flexibility or for as many states as you can go, prefer to use Moore machine. But if you are tight on timing or so forth and you have to modify your design, then you can design Mealy machine, but with very careful considerations of these outputs, combinatorial outputs here, right? As we discussed just now, Mealy machines react faster to inputs, okay. So as soon as there is an input change in the input, it will quickly react and the output will be changed. It will not wait for the clock edge. It will right away change the output as soon as the input is changed. Well, there are going to be some delay, combinatorial delay, but that's okay. We are not discussing combinatorial delay here, but you can analyze with timing analysis tools how much delay is going to be there and whether it is meeting your circuit timing or not. And as we discussed, it might lead to asynchronous feedback paths, which is quite tricky. So you must have to synchronize these outputs if you're going to use that output as a feedback path. So we discussed this back-to-back synchronizing method in one of the previous lectures. So if you have not watched, or if you are not familiar with synchronization, you may watch that previous lecture, but it's just back-to-back flops. Typically we use for synchronization, but depending upon the technology, you may have to use a special synchronizing circuit. Okay, so synchronization is the keyword. Now let's take an example of a sequence detector. The objective here is to detect a sequence either 0, 1 or 1, 0 in the input. Okay. Now let's take an example for Mealy machine. How we can do that? So initially, you are in reset. As soon as reset is deasserted, you reach to a default first state. And after that, if you're and in a Mealy machine, just for convention that on every arc we say that okay, we are input and output. So we reset is input, for example, here, and what is the output produced, because you see Mealy machine is very susceptible for input changes because it make use of input to produce the output, state outputs. Okay, so now if there is a input 0, okay, we are detecting 0, 1, it moves to a next state and producing output 0, because it will produce output 1 only if the sequence detector detects the sequence 0, 1 or 1, 0. Okay, now for example, output goes 0, it moves to the Q1 state, and if output goes to 1, it goes to another state, right? In the same way, we can construct the whole state diagram, full state diagram for this small sequence detector. So let's say after Q1 state, we detected 0, okay, on one clock. Next clock, if it is 0, 0, then be in that state. However, if there is a 1, then it means that we detected the sequence 0, 1, okay, and we detected the sequence 0, 1, input is 1, and we produce the output 1, and we move to the next state, that is Q2. Okay. All right. Now in Q2 state, we can get input 1. Okay, so we will be in 1. Okay, or if we get 0, then we move to state Q1. Okay, so let's say if we have 1, 0, then say we have identified 1, 0 in this sequence, and we have output 1, and move back to the Q1 state. Okay, so this is a very fairly simple state diagram. Okay, now our objective is to design digital circuit. Okay, so how can we encode these states and make use of flip-flop and combinatorial logic to produce the output? Okay, so let's take next step, that we fill the entries in the state table. Okay, state table is nothing but this is your graphical representation, and in state table it's just you are filling up the entries in which state you are. Okay, so initially you are in reset. Okay, reset state, we are assuming active low is the reset, so means when reset is 0, your machine is now in working condition. So when the reset is 1, everything is ignored. Okay, and then you're gonna move to state Q0, which is the default state. Okay, so next state will be Q0. Okay, now in the Q0, as we discussed, if input is 1, current state is Q0, is going to move to the next state Q1. Okay, and what's going to happen to the output? 0. Now if the input is 1, okay, its current state is Q0, and it goes to the Q2 state and output is 0. Same way we can do all entries in the table. Let's take this entry, interesting entry, where we output 1. So the input is 1, okay, and we are in state Q1, okay, and input is 1. So we have detected 0 1 sequence and we output 1 in the same way for the other one, and we fill this whole entry for all the possible states we are in and the input what we are receiving. Okay, fairly simple, fairly easy, not much complication. Now let's talk about Moore machine. So there is a little difference in the state diagram for Moore machine. Okay, so as we said earlier, that Moore machine, the outputs are dependent on the function of the state only. Okay, so what it means that you have reset, input reset, and you are in by default Q0 state, and because you are in Q0 state and you have not detected the sequence yet, so see in the state diagram circle we are representing state as well as the output of that state, while on Moore machine we were representing the output on the arc along with the input. Okay, minor difference in state machine diagram. Now let's say we get 0 on the input, so we move on to the next state Q1 and we output 0 because we have not detected the sequence yet, and then or from Q0 state we might get a input 1 and we move to the Q2 state and we give out the output 0 because we have not detected the sequence yet. Now what happens if we are in Q1 state and we receive 0? So we just be in that state. It's very similar to Moore machine's Q1. Okay, and we output 0 here. Now if we detect here 1 on the input, means that we detected 0 and 1 and we move on to the next state. Okay, and that next state we move and then we output that 1 in that state that we detected 0 and 1. Now after that, if we detect 0, okay, onto the next clock edge on the at the input, if we detect 0, we move on to the next state and we say that okay 1 0, we detected 1 0 and we output 1 in Q4 state. Okay, now it can also happen that after detecting 1 0 0 1 1 0, we are in Q4 state and then we find 0 at the input, so we go back to the Q0 state and we are in this state until we detect 1. Or it also can happen that after detecting 1 0, we are in state Q4 and we receive at input 1, so we go back to the Q3 state. Similarly, we can complete this state diagram, right? So interestingly, now you can see here we have more states. Okay, we have more states in Moore machine because we are not using the input to produce the output. Output is produced only in the state. And if we have to complete the state table, how we can do that? Let's see here. Reset, input current state, next state output. It's very similar like we did for the Mealy machine. That okay, now we detect input is 0, we are in a state Q0. Okay, we detect input 0, we move on to the Q1. Okay, and we output 0 in that state. Okay, now we can fill up all these entries. Let's say we are in state Q0, we receive 1 input, we move on to the Q2. Okay, we are in Q1 state and we receive 0 at the input. Okay, so we remain in the Q1 state. Now interestingly here you see the output, 4 times we are producing output here. Why? Well, it's simple. Say we are in Q3 state. Okay, we are in Q3 state, and in this state we output 1, and if we receive 0 we move on to the next state Q4. So you see here we need a state to produce an output. An output will be produced on the next clock edge, means our state machine will go into the next state. Same way we can fill up entries for let's say in Q3 and input is 1. We are in Q3, input is 1, we move to the Q2 state, and we are in Q3, we output 1. So see the difference in Mealy and Moore machine. So the fundamental difference, very little fundamental difference, but that little fundamental difference makes a big difference in the circuit realization, or when you're going to synthesize your logic circuit, it makes a big difference. Okay, two variants. Now let's take another example, very simple example of a vending machine, right? So let's say our hypothetical vending machine, it has a coin sensor and it takes a dollar coin and half a dollar coin. Okay, and we have to design this vending machine FSM, which takes, clock is coming, reset is coming, $1 coin is the input, so we represent it by D, let's say, and half a dollar, 50 cent, we represent half a dollar by H. Okay, these two inputs, and so once this machine receives $1.50, it will there is a mechanism for open up the tray and releasing the bottle of water for you. Okay, very simple. So now let's see how we can realize it in a state diagram. Initially reset is there, vending machine, there is nothing, no coin, 0, balance is 0 cents. After that, if you put a dollar, machine moves to a state where it is counting dollar. Okay, and if you are putting a 50 cents or half a dollar coin, we represent that input by H, the machine moves into a, let's say, 50 cent state. Now after that, after 50 cents you can put one more 50 cent coin or half a dollar coin, and machine moves to the $1 state. Okay, or you can also put a dollar after putting 50 cents, and from 50 cent state your machine now moves to $50 state. Okay, and the machine opens up the tray and your release mechanism works and you get the bottle of water. Same way when machine are in $1 state and you put half a dollar coin, 50 cents coin, and machine gives you the water. Now this is a very simple hypothetical example. Remember, in this example we are not considering about error scenarios, what happens if you put $1 and $1, $2, machine is gonna give you money back. No, we are not considering, otherwise machine will be more complex, and it will be difficult to make you guys understand. So let's start with a very simple example, and then you can make this machine as complex as you want. Okay, so this is a very simple state diagram, okay, for this machine. All right, now we can talk about the Mealy and Moore variant, but more or less the state diagram would be very similar, except how the outputs are generated. But let's talk about this diagram and how we can synthesize the state machine. Okay, so let's try to fill up this in a state table. Okay, so a typical state table, we have present state. So how many states we have? 0 cents, $1, 50 cents, and $1.50. 4 states. Okay, 4 states. Now in each state we have two inputs. Either we can receive input dollar or half a dollar, D or H. Okay, so what possible combinations would be? 4. Okay, two inputs, 4 combinations, 2 to the power 0 1 0 0 0 1 1 0 1 0. Same way we can have 4 input combinations for 50 cent state, and same way for the $1 state. Now in the $1 50 cents state, we just receive the bottle of water. We don't put any money, or the machine don't care about any money because it has received the money required for 1 bottle of water, that is $1.50. Okay, so we just ignore the inputs or don't care. It becomes a don't care. All right, now when we are in 0 cent state, if the $D or half a dollar H, DH or 0 0, our next state would be the same. We don't do anything here, machine doesn't do anything. Now if you put in half a dollar coin, then machine moves to a 50 cent state, and it doesn't open up the output tray because it has not received $1.50, which is required. Okay. Now you can input $1, okay, and you are in the current state is 0, so you move on to the $1 state. So this table is very similar to the state table what we discussed just a few minutes ago. So what we are basically translating this pictorial representation in a form of table, okay, for better understanding, and so that we can assign some state decoding logic and logic to get the output, and we can create a logic circuit. So after creating the state diagram, the second step is to create a table, state table. So I hope you guys can fill it up, all the entries. Let's say we are in 50 cents state, we can receive half a dollar, we move on to the $1 state. Okay, we are in 50 cents state, we can receive a dollar, we receive a dollar, we move on to the $1 50 cent state. Okay, and here we are assuming that we are talking about the Moore variant. Okay, in this state table example. Okay, as you can see here, after putting a dollar, and we were in our machine was in 50 cent state, it reaches to the state $1.50, and it doesn't output anything. It waits for the next clock edge, and it is in $1.50 state, and in that state it outputs 1. Okay. So $1.50 was our output tray or final state, and $0 was our reset or initial state. Okay, and in between we have these two states, $1 and $50. We can fill it up all other entries. Good. So we got the state table. Now let's try to understand how we can put coding onto these states. So as we know, we have four states. Okay. Now in binary, how much minimum flip-flop would be needed if we just want to use binary encoding? So 4 is equal to 2 to the power 2, and in binary, because we have base 2, 0 and 1, so we need at least 2 flip-flops. Okay. So we need at least 2 flip-flops. So let's say, what do I mean by 2 flip-flops? Say we can encode the state 0 cent as 0 0, okay, and 50 cents as 0 1, $1 as 1 0, and $1.50 as 1 1. Now here 0 means 0 0 means Q0 Q1. It's you may think of it as we have the flip-flops, Q1, Q0, and the state of your machine or circuit is stored in these flops. Okay, Q0, Q1, and same way you can say, okay, next state would be my D1 and D0 here. Remember, the next state D0 D1 means the state on the next clock edge, means that would D1 becomes the input for this Q1 flip-flop, and the Q1 becomes the current state or present state. So we didn't change anything, we just put a label, or we just encoded our states in a form of binary state encoding. Okay, and same way, we can say next state, we just encode it. So this 0 0 0, 50 cents, 0 1, $1 1 0. We didn't touch anything, and in the end, we are outputting in the state 1 1, and output is 1, means open the tray and give the water. Good. Now, is that the only kind of state encoding, or is it preferred? Maybe not, because see here, sometimes your two inputs are changing. See, if your machine is moving, and if it is binary encoded, it has to change 2 bits if it is going from 0 1 to 1 0. Now, since two inputs, it is jumping, two inputs are changing at the same time, there might be a risk for glitches. It depends on technology and what kind of what are delay requirements for these circuits. But at the bottom, it's a risky behavior. Okay. So in practice, what we do, we typically use one hot encoding, or if you have to use binary encoding, then in some form you change it to gray coded gray encoding and all. But say if you are using this encoding within one clock domain, you are fairly okay, you might get away with that. You don't have to worry about. But let's say if your state machine is being used say in FIFOs, um, or say producing some logic which is being used in different clocks, or this machine is making use of inputs coming from different clocks, clock domains, you might have to reconsider your design. So in practice, it is best only to change one bit at every clock edge, especially for the state, because that's the inherent structure of flip-flop design, how D-flops or other sort of flops they work, that they suffer with the metastability, and if the flop goes into metastability, we can't rely on the output. So a bunch of things, we are not going to discuss all those things there, but just to give you an idea that beware of or aware of what kind of encodings are. So we have another kind of encoding, we call it one hot encoding. What is the difference here? Say you have more number of flip-flops. If you have 4 states, you have 4 flip-flops. So think about, if you have a 1000 states, you might have to use 1000 flip-flops. For one hot encoding means only one flip-flop, one bit is set, which is indicating that state. So for Q1, if Q1 is machine is in Q1 state, means Q1 is set, Q1 bit is set. Okay, and if it is all 0 0 0, you may think of as a reset state. Okay, so this is one hot encoding is fairly simple. Say we have 4 states and we have 4 flip-flops, and each bit is set, which is representing each state. Okay, it's fairly simple. We are in this state, say 0 0. So 0 0 means we are in Q0 state and one bit is set. Now we are in Q2 state, so second bit is set. Okay, second bit is set. We are in Q3 state, okay, third bit is set, and we are in Q4 state, fourth bit is set. Okay, fourth bit is set. So we don't have to worry about all other flops because only one bit is changing at one time, which is being used in our combinatorial logic or other places in the circuit. Okay, so remember that distinction, what is one hot encoding and what is binary encoding. Okay. Here for explanation purpose, I would be using binary encoding, okay, to make you understand, but you can also go ahead and try the same examples with one hot state encoding. Fairly simple. Okay, so let's try to understand the Moore machine. So we already have this binary state encoded table. So what it is? So as you can see here, we have 2 flip-flops, okay, 0 and 1, and we can make use of these 2 flip-flops to design the circuit. How? Simple. So essentially what it is that we need to know in some way what should be at the input of this flip-flop and at the input of this flip-flop and the output. 3 things. That's it, and we are done. Okay, we have input capital D, capital H, these are inputs. Okay, and also the states in which our circuit is, that is state which is stored in these flops. Okay, so these goes to our state decoding logic as well as producing the output. Okay, so now if let's say we want to develop for D1, so let's say D1, wherever D1 is 1, those lines. Okay, so D1 is 1 here, D1 is 1 here, sorry, D0. So D0 is 1 here, D0 is 1 here, and D0 is 1 here, D0 is 1 here, D0 is 1 here, and at the bottom. So as you can see, one way is that you add all these and form an algebraic Boolean equation. Okay, so what it means that Q0 Q1, Q1 bar, Q0 bar, and D bar and H plus this combination, which is Q1 bar, Q0, D bar, H bar. Okay, and so on. We can keep on doing that. or we can also try Karnaugh map. Okay, so let's try Karnaugh map for D0, right? So as you can see here, we have D0 1 here, and at that we have Q1 and Q0 0 0. So Q1 Q0 0 0, okay, and what is the value of D and H? 0 and 1. So 0 0 and 0 and 1, and we made entry 1. Okay, now next, you see here the dash, it means the don't care thing. We will make use of it as we like it. Okay, now next would be, say here 0 and 1, where the Q1 Q0 is 0 and 1, and D and H are 0 0. So we made that entry. Now this one 0 and 1 and 1 and 0, 0 and 1, 1 and 0, we made that entry. And now this was, say, don't care, and don't care we use to minimize our Boolean equation. So we can make use of it in the very end, how to minimize that. Okay, now let's fill up all the entries. So we were here, so 1 0 and 0 and 1. So Q1 Q0 1 0 and 0 and 1, we made that entry. And then here 1 0 and 1 0, 1 0 and 1 0. All right, that entry. Now in this entry, see, it's interesting, D and H both are don't cares. Okay, and Q1 and Q0 are 1 1. Okay, so Q1 and Q0, so we get this row, sorry, this column. Okay, because D and H both are don't care, so we fill all the entries. Now these entries, one for this don't care, where Q1 and Q0 are 0 0 and D and H are 1 1. Okay, and the don't care was here, Q0 Q1 0 and 1 and 1 1. Okay, and another one was here, which is this one. Now how do we minimize that? Well, as you can see here, we can make use of this combination. Okay, this will give us Q0 Q0. Okay, Q0 is 1, not changing. Okay, and from this side, now we can also make use of this little block here, and we can make use of this thing here, and we can also make use of this thing there. Okay, so what essentially we can find after solving this Karnaugh map, the equation for D0. It was very simple, that say D and H. Okay, so we make use of all this, then it means D is stable here, and if we go from here to here, so Q0 here to here, Q1, because Q0 is changing, so Q1 D. Okay, in the same way we made use of this 4 1 1 and 1 don't care, and we got Q1 and H, and we made use of 1 2 3 4 these 4s, and we came up with the Q0 Q0 Q0, same, and H bar. Okay, and H bar. Okay, H is 0, same way Q0 bar and H. So you see how we have mapped, okay, the information from this state table for D0 into a Karnaugh map, and from Karnaugh map into an algebraic Boolean algebraic equation. If you don't want to use Karnaugh map, then you can solve Boolean equations, set of Boolean equations, and finally you will arrive at that equation. Okay. Same way we can solve for D0. Okay. We can fill up the entries for D0. Okay. So what will be for D0? Sorry, D1. So we already did for D0. For D1. So D1, where is D1? 1. So we're gonna be considering at this row, and then for D1 we're gonna be considering at this row as well as this row. Okay, this row, this row, this row, and last row, and along with all don't cares if we need to use them. Okay, and we fill up all the entries in this Karnaugh map as we did for D0. Okay, and we arrive at that equation, D1 equal to capital T, which is dollar, plus Q1 plus Q0 into half a dollar, that is H. Okay. Now the output is very simple. We have just output in only in one row, very end row, and what it is saying that we are in state 1 1, and we just need to output 1. So it was very simple. At open tray, when you are in state 1 1, 1 1 means Q0 and Q1 bit both are 1. Okay. Now let's put these equations in terms of gates, logic gates. Fairly simple. It looks like a big diagram, but it's fairly simple. Say we found the equation for D1, okay, and we implemented this little circuit for D1 where D is straight coming, plus means OR Q1, Q1. So I didn't connect from here, otherwise basically this is gonna be connecting to the Q1. Okay, so don't worry, otherwise circuit diagram will look like a bit messy. So instead I just use the label Q1. Okay, and then Q0 and H, and of Q0 and H, so Q0 and H. Sorry, this is not, this is Q0 and H. Okay, so that's the right one. That connection is not right, so let's delete it. Let me take, this is Q0, Q0 and H. So we made this connection here. Okay, and 3 input AND gates. So if your technology library doesn't support 3 input AND gates, you can make use of, you can convert this 3 input OR gate into AND gate, or other logic gates. So this is here just to explain that we are using 3 input OR gate and AND gates. Now here for D0 it's a bit complex circuit. See here we are doing the OR operation for 4 terms, 1 2 3 4, 4 terms. So 4 input OR gate going to D0. Okay, so Q1 D, so this is our D, and this is our D, and Q1 D. Okay, and Q1 in H. Okay, this is our H, Q1 is going here, and then Q0 H bar. Now Q0 coming here in H bar. This white circle is nothing but indicating a NOT here, NOT gate or NOT operation, and same way here Q0 bar and H. Okay. So this is H bar and the Q0, and here Q0 bar and H. Okay, and we got this open tray, means the output Q0 and Q1 output, we ANDed it together. Okay. Now notice here that the output is now using a combinatorial block, which is an AND gate. Okay. Now if you are using this output within the same clock domain, it's okay, but if you are sending this signal from this clock domain to another clock domain, you must have to synchronize this signal. How? We discussed many times, back to back flip-flops or a synchronizing circuit which synchronizes this output, which is the AND operation of state Q1 and Q0, into the receiving clock domain. Right? So be careful with the synchronizing part. Now that was the variant for Moore machine. In the same way, we can design the Mealy machine. For this small vending machine example, the only difference is in the output for Mealy machine. D0 and D1, all other states are same for this example, small vending machine example. So what it is here, that see here, as soon as the input is changing, okay, input is changing, that say for example you are in 1 1 state, okay, your present state is say 0 and 1, okay, and your input you are putting a dollar, so and you are moving to this state 1 1, and as soon as your input is changing, you are changing the output on the same clock edge. You are not waiting for the next clock edge, on the same clock edge. Okay, so we are putting 1 here in the state table. Same way we can fill it up other entries for the table. Let's say you are in state 1 0 and you receive or the machine receives 50 cents. It will move on into the state 1 1, outputting 1 or opening the tray. So our output tray or open the tray output function will change, and how it is, we can fill it up in the Karnaugh map, and we can solve this Karnaugh map. Easy peasy. We can solve this Karnaugh map as we did earlier, and we get this function. After getting this function, we make use of previous all these previous circuit, and now in the previous circuit it was Q0H, so it is Q0H. That was by mistake, I connected with the T0, so don't count it. All right, good. So that is connected here, Q0 and H. Okay, so that's the path. Q0 as that AND gate, and that is representing here D1. Now interestingly, say we are making use of Q0 and Q1, that AND gate and output of both states, plus extra is input D and Q1, put D and Q1 ANDed together, okay, and then Q1 and H, Q1 and H, okay, and Q0 and D. And for input OR gate, that is our open tray output. Okay, now here you notice that for the output function, not only we are making use of states Q0 and Q1, but we are also making use of inputs D and H. It is very important for you to understand this, that now this input is It is changing as the input is changing, this output is changing. Now to make sure that you do not open up the tray, okay, so after that you AND that this output open tray with reset. It will make sure that when the system machine is under reset, it will not open up the tray. Okay. Nevertheless, be careful when you're gonna use that output somewhere. If you're gonna use as a feedback path, it must have to be synchronized, or if you're gonna use that output to some other blocks where those are working on different clock domain, it must have to be synchronized. Okay, so that's a variant of Mealy machine and Moore machine for this small vending machine example. Okay. Now, so we discussed so far binary encoded. In the same way, if we have one hot encoding for these states, it becomes so it becomes easier for one hot encoding to visualize these equations which are for next states or the inputs to the 4 flip-flops. Okay, so as you can see here that D0, when D0 is 1, we get only one row here. Okay, and in that one row we say, okay, Q0, only one state has to be set, Q0. Okay, and what happens to the outputs? Well, DZ is 0 and H is 0, so D bar and H bar. In the same way, we can get equations for D1. Okay, D1 is nothing but the second one, so we get this row for D1, and where else we have D1? This row. Where else we have D1, 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 D1? Good. Now, so Q0, here we have Q0 and H. Okay, we make use of this H. And if we consider this don't care, we don't have to think about D because it becomes now don't care. So we get Q0H, and what do we do? Plus for this second line, Q1 and D bar and H bar. Okay, you can solve it using Karnaugh map, but I'm just sloppy here, so quickly did it that way. But if you're gonna use Karnaugh map, you're gonna end up getting the same equation. And for the open tray or the output, when we are in Q3 state, we just issue the signal to open up the tray or output the signal. Okay, very simple. And in the same way, like we did, we can design its circuit. Okay, now wonderful, we did all good. Now, interestingly, these machines are very simple machines. Think about if there is a complex circuit. Okay, you guys might have to write verilog code or VHDL code for designing digital circuits. So let's take an example of a verilog code for Moore machine and Mealy machine. So let's talk about firstly Moore machine. So this is a verilog code for vending machine Moore version, and these are, if you are familiar with the verilog programming language, these are by default you would be knowing that, okay, we need inputs and outputs. Okay, so clock, reset, H and D are inputs, and open trays are output from this machine. Good, so we specified input and output. And now this is important here. Okay, so most of the time in ASIC design, you're going to be using synopsis tools. Okay, and by specifying parameter 1 colon 0, you are saying tool to encode it in a binary encoded way. Okay. Now if you specify here say 3 down to 0, okay, and you assign these states as 0 0 0 1 and you specify those parameters, it will make in a binary it will make in a one hot encoded state. Okay, so this example discusses the binary encoding, but that's the only difference here, how you specify the parameters. Okay, so if you specify parameter 3 down to 0 and say 0 0 state 1 0 0 and the next state 0 0 1 0 and so on, you can fill it up. So tool will understand as long as you have put synopsis enum code, it will give you one hot encoded, otherwise in this way binary encoded. Okay, and register open tray. Okay, now that's again it's the keyword synopsis to guide the synopsis tool, that now it is our state vector, state and next. Okay, so that the tool will not mess around with our code. Now this is important that you have this state. Okay, so this will become the register. Okay. So that becomes the state. Okay. And next, this is next. So you see we have one always block here, which is just simply saying that if you are in a reset, just stay at the 0 state, otherwise move to the next state, means register this value of the signal next. Okay, and make it a flip-flop. Now this is a second always block which will have all the inputs. Okay, this is very important. You should have all the inputs which are participating in state decoding logic, D, H and state, okay, in the second always block. And you write case statements in whatever state you are in. If you are in 0 0, you write associated logic for that state, and you will further write the logic. Okay, now that is the distinction to show how the Moore machine will differ from the Mealy machine. So after your combinatorial block, now you have another combinatorial always block here, which is basically saying that if there is a state transition, you would output the state. Okay, you would output in the state 1 1, that is 1. Okay, and the state gonna change on every next clock edge. Okay, so you're gonna receive the output on next clock edge when the input changes. Okay, so that's a difference in the Moore version of the machine. Now let's talk about, so here we have used C3 always block. Always remember that registration of your states or memory elements, try to do in one block, one always block, and all your combinatorial logic in another block, or state decoding logic, okay, and your output logic if you are using Moore machine in another always block. So that is, your code is cleaner, tool will understand it in a clean way, and you will not get further problem in synthesizing the larger, bigger circuits or even smaller circuits. That way you will make sure that you will design synthesizable digital circuits. Okay, if you want to simulate there, and if simulation tool needs some special delay and all, you can specify that, specify using delay directives in Verilog just for simulation purpose. Okay, like this before before any assignment if you have to, but for synthesis it doesn't make any difference. All right, now let's talk about Mealy version of the state machine. Okay, so what it is, see, everything is same, all parameters and whatnot, all specification is same, even your always block where you are registering um, the states, or making sure that the state transitions are stored, sorry, not state transitions, the state is stored in memory element using this always block, and here specifying like that. And in the second always block, since in Moore and Mealy machine, your outputs are function of inputs as well as the state. So as soon as any input changes, okay, as soon as, let's say, any input changes, you put a condition and you change the output, okay, and change the state. So when the machine will move on to the next state, it will also output. That means that I'm going to 1 state and I'm outputting open tray 1. The same way you can fill it up all other entries for, or all other associated logic for other states. Okay, so that's the difference. Now tool will understand if you write logic in this way which one to implement it. Okay, cool, good. So just to make sure that when you write code, Verilog or VHDL code, make sure that your code is cleaner. You have separate always block for sequential logic, okay, or registering part of your digital circuit where states are registered, and a separate part for combinatorial logic. Okay, and if you have to register this, say for example open tray output, if you have to register, you can write one more always block for registering that output, and bunch of other things you can do. Right, so that was the basic and fundamental idea about how to design state machines. Okay, if you guys have any questions, if you need any help, feel free to send me an email. You can also have private consultation, private tutoring. Just send me an email that you did not understand that thing and you want to have clarification, or any thoughts you might have, or any other topic you would like to discuss. I might create lecture for that topic. So I hope guys you have enjoyed this lecture, and thank you very much for liking LeProfesseur on YouTube and subscribing LeProfesseur channel on YouTube. Have a wonderful day.